Okay, let's get into this. We're going to start talking about reactions, and we kind of want to think about how ionic compounds are going to behave in solution. We've talked about electrolytes already, so we kind of have a little start of how this is going to work. Um, but yeah, we're going to think about hydration, and we're going to think about solubility and how this stuff works in helping things happen in reactions. Okay, in terms of hydration, what we're thinking about is getting the uh, excuse me, getting the ions into solution. And what happens here, this is all due to the ion dipole forces, that nice intermolecular force that requires an ion and a polar molecule. Okay, this is why water is such a good solvent for ionic compounds. It's a very polar molecule and it goes in and so you can imagine here a solid crystal of, say, sodium chloride, and you put it in water. The water molecules come in, they attract the chlorides and the sodiums. Notice in the chloride, the positive end of the hydrogens are grabbing onto the chloride. On the sodiums, the negative end of the water grabbing onto the sodiums, okay, and they're pulling them into solution. Okay, we're going to think about this from, right, this is going to work. Okay, so we're going to think about this in terms of solubility. Um, Solubility officially is the max amount of solute that's going to dissolve in a given quantity of solvent. This is temperature dependent. What we're going to look at now is how can we predict whether or not ionic compounds should be soluble or are probably not soluble. We'll expand on this idea later in Gen Chem 2, but for right now, we're going to just think about this. Okay. So our idea here is if we have ionic compounds, they're either soluble or insoluble. If they're insoluble, then they're going to exist as a solid. They're not going to do anything. They're just going to kind of sit there in the whatever and do their thing. Okay, not really do anything. If they're soluble, then they behave as a strong electrolyte. They go into the aqueous phase and they completely dissociate. So we really only have two options for ionic compounds: insoluble, where they're sitting on the bottom as a solid, and aqueous, where they are completely dissociated. Okay. All right. So in terms of how to figure this out, okay, we're going to use what are called the solubility guidelines, remembering that all these things are strong electrolytes. If the ionic compound is soluble, it is a strong electrolyte in solution, which means it completely dissociates into ions. We kind of want to remember this thought. Our strong electrolyte completely dissociates into ions, and this all is all soluble things in water. Okay, so if you're an ionic compound and it's soluble, it's a strong electrolyte. Okay, so what we want to do is we're going to use our solubility guidelines to determine what things are soluble or not soluble. Okay, that's kind of where we're at the moment. Um, and our rule here is if one of the ions in the compound is soluble, then the compound is soluble. They don't both have to be, only one has to be. This is how the chemistry is going to help us do things. Okay, these are the solubility guidelines from our textbook. Um, they're okay. I mean, they're basically the same kind of idea as what we're talking about. Um, these are the solubility guidelines I'm going to give you on the exam. So this is what we're going to be working through. You'll get a handout with these on them as we do it. Okay. So this first rule, I don't have it on this because I don't give you this rule on the exam, but the first rule of this is you want to know what the always soluble ions are. Okay. There are 10 of these, and you have to know what they are. They're the same ones that are listed here in the table from our book, right? All of the group 1A, okay, and NH4, ammonium, and then nitrate, acetate, chlorate, and perchlorate. Okay, perchlorate's not listed in the book, but perchlorates are mostly soluble. Okay, if we know those, any compound that has any one of those ions in it is going to be soluble. Everything else is going to have some uh, insolubleness to it. Our big thought, what we want to remember and think about, is that Ionic compounds tend to not be soluble. You know, there we go. Not to be soluble. All right. So if you've got an ion in your compound that makes it soluble, it will be soluble. Okay. And we've broken these down into uh, two main categories for us. The first one are the ions that are usually soluble. Okay. Chloride, bromide, iodide are usually soluble. Sulfate is usually soluble. Chromate is usually soluble. Okay. We're not going to stress too terribly much about chromate, but I'll throw it in there because it's in our book too. Um, exceptions here generate insoluble compounds. So the exceptions are going to make solids. So silver, mercury, and lead are insoluble halides. Strontium, barium, mercury, and lead are insoluble sulfates. Okay. Silver sulfate is mostly soluble. So I consider this to be soluble. And when we work with it in lab, it turns out to be soluble. So that's how we're going to kind of go through that, even though our book says it should be insoluble. Okay. The other two examples here on our list are usually insoluble. Okay. Um, and so their exceptions will generate things that are aqueous. And those are sulfide things and hydroxide things. The nice thing about these two is their exceptions are all the same thing. Ammonium, calcium, strontium, barium, and group 1A are soluble. What's nice about these is that most of these, ammonium and the group 1As, are always soluble, and so we don't have to stress about that. Just calcium, strontium, and barium tend to be soluble with hydroxides and sulfides. Okay. Now, the big test is, can we put this to work, right? Can we look at a compound and decide if it's going to be soluble or insoluble? Okay. Look at this. You might want to have your solubility guidelines handy. Okay, if we have lead 2 sulfide, sulfides are generally insoluble. Lead is not an exception, so this is insoluble, which means we would write solid if we're doing a reaction. Okay. If we look over here at sodium carbonate, okay, carbonate we don't have a guideline for, which would mean that carbonate should be insoluble. However, sodium is one of our always soluble ones, so this is soluble. If you see this, this should be aqueous. Okay. If we look at silver bromide, bromides are usually soluble. However, silver is an exception, which means this is insoluble, which is a solid. Okay. If we yeah, if we look at calcium iodide, iodides are generally kind of soluble, right? That's our halide rule. Calcium is not an exception for that, and so this is soluble, which is aqueous. Okay. If we look here, we have calcium phosphate. Phosphate is one of those ones we don't have a rule for. Phosphates are generally pretty insoluble, but if we don't have a rule for it, you can treat it as insoluble. Calcium, again, we don't have a rule for either, so this is also insoluble, so this is insoluble, which means it's a solid. Okay, which is good because our bones are mostly calcium phosphate, and so are our teeth, and so it would be bad if those things dissolved. Um, Lastly, we have this guy, vanadium 5 acetate. Even though this is a weird thing, we can figure it out. Vanadium, we don't really know. There's not a rule for this, so it's probably not very soluble. Acetate, however, is always, and so this is soluble, and we would call it aqueous. Okay, get used to this. Practice, practice, practice. Remember, you don't have to know all of the solubility guidelines, right? You're going to get this on the exam. Maybe not chromate, but you're going to get this on the test. Okay, what you're not going to get are the always ones, so these are the ones you want to commit to memory. Okay, alrighty. If you have any questions or need me for anything, just let me know. I'm here. I can help. See ya.